There's a new in class number 9 for today. If we couldn't finish it, we'll keep working on it on Tuesday next week. So the softcore is a very big part of this class. It's a Picoblaze microcontroller. You can synthesize and implement it on your IPGA. You can put your assembly coding. If you have taken microcontrollers with Dr. Wee, or you probably have done a lot of assembly coding with microcontrollers. You can send signals to the ports and do interrupts and a lot of things similar to the C programming to the MCUs. It's pretty powerful. And so we'll do that today, and next week we'll cover a midterm review and a little bit more about that. And then Thursday next week will be the midterm exam. Okay. And then the week after, we'll talk more about it. I think there are more details about the instruction sets of it. And next Tuesday there's a lab, right? There's a lab with it. So the lab will be a 2-week lab on that microcontroller implementation. Wait, it's a different link. It's a wrong link. Okay, it's over here. Okay. It's a little bit calculator. Because microcontroller has a CPU in it, so we could do more complicated calculations. This is doing a square and addition. Square and addition. With some multiplication involved. So that is why we need a CPU over there. So using software to program it makes it a lot easier. Because if you just do it in hardware, I haven't done that before, but how would you do multiplication with Verilog?
You do like shift add with bits.
Yeah, you can shift, right? It's a times 2 times 3, yeah. So it's not that convenient, right? So the C programming, you can directly use the multiplication, the asterisk, to do it. And I mean, for the assembly, and there's a way to do that as well, right? So it's doing a square. It's also doing shifting as well, I think. But definitely, it's more flexible because so the instructions are software, so you are able to jump to different locations. Like the C programming, right? If you call a function, it directly jumps to the sub-function. Similarly, in assembly, if you do a jump, right? Like jump, NC, then it jumps to a subroutine over here. And so by checking all the flags, it could be a C and a Z. So look into the flags really quick. It's behaves like an if statement. So imagine it's actually looking at the flags. If it is 1, then do something. If it's 0, then do something else, right? So this is like an if statement. So that's how you do it in the assembly coding instead of in C. And so I believe you guys already took architectures, or have you? You have? Everyone? No, you haven't? But have you done assembly before? Even a little bit? Have you? Tiny little bit? Yeah. I didn't use assembly for my microcontroller class because when I was in college, I did that, right? So a lot of students just lost their interest because it's just so boring. And you couldn't develop a massive scale project based on assembly really quickly. So it becomes very boring really quickly. But the thing is, you can learn the bottom level instruction sets and the interrupts and register level stuff really well. But in real world, usually developing a system level project, if you look at senior SEM projects, none of them have developed their project using assembly, right? So it's all, if it's Arduino based, doesn't matter if it's a BSc major or a C major, they all use C, right? The C. Or if it's on the Raspberry Pi, it's going to be Python, right? So we don't really use assembly for high level R&D. So, but bottom level, it's good to look into the architecture of the system. So this is what we are going to do here, right? So for IPGA programming in the future, if you implement a little microcontroller to the IPGA, and there are also options like a C compilers that are available for you guys to use. So you implement the core onto the IPGA, and there's available C compilers that I can directly program in C, and then compile it and then download it to that microcontroller. So it's very similar to a regular Arduino chip. It's very, very doable. So we don't have that compiler for our Basys board, but there's a bigger one called Zat board. It's also from the same company, also from Xilinx and Digilent. We have a lot of board in the lab. If you want to play with it, let me know. So these ones, they do have an ARM core on it, and you can program them with C. Okay, so you have a compiler to do that. It's very powerful. Okay. So now let's go back to our tutorial. So you can see that for the next few weeks, including the spring break, and so we'll have a midterm exam next week, and then it's gonna be the spring break after, and then the week after will be a little bit more about the Picoblaze microcontroller as well. So you can imagine for the next like 3-4 weeks, will mostly just about microcontrollers, right? Including this week, about 3 weeks, including the break. Okay. And after that, we'll do our SPI. Takes a week, and then our ADC. Then we'll just keep working on our course project for the rest of the semester. We'll develop a oximeter. It's a little sensor outputs digital data, analog data, and it's being digitized by your ADC on the IPGA. And then we interface with that. You put your SPI module on it, and then you communicate to a microcontroller's SPI and display it in a serial monitor, so you can plot it. Your heartbeat. You can find your heartbeat rate from there. Your heart rate from there. Okay. So that's the course project. There will be a little PCB involved. So last semester, because the students were they haven't taken any PCB design class with me, so I designed the PCB for them. But for you guys, most of you already did it in the microcontrollers. Even you haven't, but it's easy to learn. It's a very good thing to learn, actually. So I'll let you guys design your own PCB and interface with our PGAs through the SPI ports. So expect a PCB design for this course project. Okay? Any questions on this?
For the midterm, will it be should we study the in-classes and quizzes?
It's going to be everything about the quizzes and the in-class.
Okay. Will it be like VLSI with any new problems, or will it be...
Did I put new problems on that VLSI exam?
Yeah.
Sorry about that.
Oh,
I shouldn't, but it will be at least 90%, at least, right? It's all from the in-class and quizzes. If there's a new problem, I'll let you guys know what the new problem would be, right? Wouldn't be just totally new. Okay? I'll let you guys know. So I'll talk about that during the review session on Tuesday, on the 3rd. Okay. All right, so let's go to the softcore tutorial. And this is a pretty light CPU developed by an employee at Xilinx, I think. And they had 2 different versions. There was a earlier version. It's a KCP SM number 3. And if you so this is important to know this because both materials, they are being put in a big package, zipped folder you can download from the GitHub. And if you don't know the differences, you download the number 3 version. It wouldn't work for a lot of our peripherals, so we don't really use that number 3 version. And so you see 2 different versions of code, diagrams, and packages online. And the textbook. So we have 2 textbooks, right? Did you purchase any of them? Do you have any of the textbooks? You do? So there are 2 textbooks. I usually don't require them, even though I put it as required textbook in the syllabus. It's very beneficial to have it. But where is it? Okay, so the first one, you can realize that since the beginning of the semester until last week, all the tutorials, code, and everything, they were based on this textbook. And I extracted all the information from this textbook and compiled them into tutorials. That's why you sometimes you probably didn't purchase this textbook, but you don't feel that way because everything is already compiled and posted to my website tutorials, right? And we are pretty much done with it. Can you imagine? It's a whole book. It's been done within the first 7 weeks. All the examples and everything from the textbook are already used and included in the tutorials. And now when we start looking into the softcore, that's not something included in the first one, and you can only find it from the second one. Okay, and the second one from Peng Chu, this guy, and it's a very popular IPGA, like IPGA 101 kind of class or textbook. It's being used pretty much everywhere. If they have a decent computer engineering program, most of the cases they will choose to use Peng Chu's textbook. This is a really popular one. It has a lot of really classic examples, and it can be directly implemented to the IPGA. It's really hands-on. So this is like what I usually do with students, hands-on stuff, passion-driven. As you can see, this is they use the Spartan #3 IPGA. It's a different one compared to ours. I forgot if it's the same chip, but definitely at least it's the same. It's a different IPGA board. It's a different IPGA board. If it's a different chip or not, I don't know. But they both from Xilinx. You can use Vivado to program them. So the only issue is you are not able to directly copy and paste the code from the textbook and use them on your Basys board. Okay, so that's not going to work. So you have to make a lot of modifications. So you have to understand the code first, and then you make modifications to it, and then you can run it on your IPGA. So other examples, I don't know. I couldn't remember if I included I2C, probably not. But so now we just focus on the softcore one. So the code is mainly from the textbook, especially for the labs code, right? And I already made the modifications to it. I can show you where they are. This is a really long one, so that's why it covers 2 weeks. So you can see these ones, right? These ones. That's when you instantiate the processor. So the processor is also a module. The CPU is also a module, a Verilog module. It's being described by Verilog, and when you want to use that CPU, you just treat it as a box, right? The box has ports, inputs and outputs. So those are the ports. So the CPU is no difference. You grab that CPU and place it or instantiate it in your top, and then you have a CPU for your design. And then you connect your top ports to the peripherals of the FPGA. Then you are able to give inputs like the switches or buttons, and then display the outputs, for example, on the 7-second display or the LEDs. And there will be many different ways to visualize the results from the CPU, right? If you have an operating system, you can definitely see the results from the monitor through the operating system, but we don't have it. Imagine you are doing everything from scratch. So in that case, if you want to visualize the results, everything is stored in the memory in the form of the 1 and zeros. And to see the results, you have to use some kind of peripherals to display them, right? We don't have a fancy monitor, have an operating system running on it, but we can definitely use LEDs and 7-segment display and as outputs and switches as inputs, right? But for the regular desktop, you have keyboards, you have mouse as inputs, and directly shows the outputs in the monitor, but we don't have it. So it's very good to have this kind of platform, like the IPGA Basys board has all the peripherals to show the results. So you can just think about that, right? So the final goal is to use that, put a CPU on the IPGA and use it. So how to use it? You need to give an input and you need to look at the outputs. That's everything about that. So part of the examples from the textbook, which you can see from here, they instantiated over here, and you can see. Remember the hashtag? What's the hashtag doing over here for the sub module? What does the hashtag do? Overrides, right? So overrides the sub module's parameters, right? So you can see for the UR ones, we had only one parameter to be overwritten, but for here you have three of them. They are in your ROM file, the instruction memory, and these are the parameters to be overwritten, because depending on different IPGA platforms, right? So the V6 is probably the Spartan 3 kind of IPGA board was used. The IPGA chip used for the Spartan 3 board, but you can see for ours, remember the name of our IPGA? Is that Arctic 7, right? Arctic 7. That's the name of our IPGA as a name given by Xilinx, right? So it's -7. That's why it's called the 7 series. The 7 series IPGA according to Xilinx. So that's why you want to change it to 7S over here for the name. 7S. Okay, so it won't be family S6 or V6. It's going to be 7S, 7 series. And accordingly, you make other changes for your board here as well. Like 1, change 2 to 1, and here as a 1. And other than that, because we choose to use version 6 CPU, we go to the top. You see? Make sure that we are doing the KCP SM number 6, not number 3. Okay? So the CPU core is a Verilog. You download it. I think I have links on the in the tutorials you can download. So download that one. It's going to be the number 6, version 6. So you have to use the version 6 as compiler. So I'm going to show you what are they here. If you scroll down, so you can see it won't be as sweet as Arduino programming, right? So everything has done for you on the back scene. So directly click programming, it directly programs and uploads the code to the microcontroller. So this is different. You have to do everything manually. So the way to do that is you have to just keep in mind this is important steps, right? So there are certain files from the, you see this is a KCP. I didn't have that included, but you can imagine this is like KCP SM6 _ release 9, right? Release 9. Whatever. So there might be newer versions, I don't know, but this one works. Okay, this one works. This is pretty new, like 2 years ago probably. And you go to Verilog, you can see the folder shows you these files, and for most of the files are not going to be used. Okay, but these 3 are critical. So the first one, okay, KCPSM6.v, that's a CPU file. Okay, that's a CPU file. It's a core. That's a core. That's a microcontroller's core. And you have another one. It's called _design_template.v, right? .v, and that provides you with the template of the Verilog that it can use to work with the CPU's Verilog. So let's give you some examples. And you can see some of the examples given in the tutorial are actually from the template file. Okay, the template file. So you want to keep the template file anywhere, but don't directly synthesize it because it has a lot of errors. It's not a synthesizable Verilog file for this guy. It just has all the examples, like have all the example 1 and have one piece of code, and example 2 have another piece of code. They are not just a one piece of code, right? It's just examples. So you never want to synthesize this guy. Okay, you open it up and look at the code, any of the code you want to use, and directly copy and paste and then modify it. Okay, that's why we keep this one over here. And the next one is instruction memory. Instruction memory is a ROM. Why is ROM? Because the read-only memory. We're not writing into it. It's not a random access memory. It's a read-only memory. So at the very beginning, we put our assembly code into a like .asm file, right? And that assembly code has to be placed in the same directory as where this ROM form.v file is at, because this one defines the format of your assembly code. So it's basically your assembly code is nothing else but just assembly, right, in there. However, the assembly's code, every single entry will be converted into a machine code like 0 and 1s, right? Like opcode or 0 and 1s, machine code. So, and these 0 and 1s will directly stored in a memory bank. However, memory is not just a memory, just a data in there. It has all the peripherals like address decoders, right, and clocks, all these kind of things. So that these peripherals, the combinational logic or could be sequential logic blocks, comes with your memory bank, will be compiled into one block like a memory IP. According to the format defined in here. We don't. I probably haven't even opened up this guy yet. We don't care. The thing is, if you keep this file in your directory, in this directory, like what I'm showing you guys here, it doesn't have to be in the project directory. It could be any directory, but it has to be in one directory. And then you place your assembly code in the same directory after that, and then this is assembler. You open it up. No, actually, you run it in your command lines, right? And you call this executable file, all right? And then you type your format file, and then your assembly, your instructions in assembly. It will directly compile it into a .v file, which has all the instructions and all the peripherals that are needed for it. So it's basically converted your assembly instructions into a memory.v file, okay, which can be used directly with your CPUs. Is that clear? So this defines the format. You don't have to open it up. You just have to keep it in the same directory, so it's able to make that memory.v module for you. Because it's a .v file, the instructions are, if you open up that, let me see if there's an example over there. Probably not. Okay, so eventually you'll see after the memory.v file is being formed, you've opened it up, you can see for the majority part of the code is actually just the 1 and 0s. So these are instructions, actually, instructions and data, and registers and addresses and data. So that's your assembly code that are being converted. But also it has the module, the name of the module, and the input, outputs, whatever. So this is actually a memory with all the peripherals and the data and the instruction in it. Okay, and the procedure of compiling this guy is already displayed in the tutorial. You can see I named my assembly code as prog. It's a program, like just prog.psm. So it's PSM, not ASM. So anyway, so it's a PSM, and you open if you are using Windows. If you couldn't do it in sometimes your Macs can do it as well, right? But if you couldn't do it with your Macs, you can use the desktop, live desktop to do it. So you have to get into the command line and go to CD to that directory, right? Because executable, so you can directly type the name of it, .eic, right? And then followed by the assembly code file name, right? So this is where it holds your assembly code, and this is the example of the assembly code. Okay, so holds assembly codes, and then this will create a prog.v. Remember, I told you guys a prog.v. That's the program's instruction memory, right? Instruction memory with the peripherals and the instructions in it. So in that case, after you have this one already available, you are able to include it into your design. So how do we include in your design? Like this, right? So why the name is different though? So this is your program file, right? The prog.v. You just type prog here because this is the module's name, and it does all the overwriting here, and followed by a DOT. So just make sure I understand what's going on. This is DOT, right? This is name. You name it program_rom in your top. Okay, but you have different names, and the name of your program file, and I believe it's called prog, and you just type it over here. Okay, type it over here. It's being instantiated over here, and then you rename it as a DOT, right? The DOT. And these are the ports, the ports of the memory, instruction memory, and the instruction memory .v file or module. These ports are defined by what? By which one? By this guy, right? So this guy defines all the formats, the ports, and everything for the instruction memory. So if you use this file here, you keep this file in the same directory, and eventually they will create all these ports for you. These ports. So enable address, instruction, and clock. RDL, I forgot what this is. Like read something. So inside your top, you are able to make some modifications, like adding a piece of Verilog code over there in order to interface with your peripherals on your Basys board, right? So you can see here, I just added another OS block at the very bottom of the top module, and whenever the write strobe, whenever the write is ready, right? So when it's 1, we do this. So this all came from the example, right? It shows you like whenever your data is ready, then this is the flag, right? So when it's ready, you assign the outputs data to LEDs. So it basically shows you all the LED as an output from your code. Okay, and I think for the very first example, we just make it super simple. Like I think this is assembly code over here, and it inputs. So whenever you use the input instruction, it interfaces with the ports. So the second argument will be the port ID. They are using the port 00, and they give the port to S0. So S0 is a register. It stores the port ID, and then it outputs whatever data being sent through the 00 input to the register, and directly output it to another to the outputs output ports here directly, and these are shorted to the LEDs, and then jump back to the loop. So it's basically just sending the input to the output. And what we did over here on the top is we connect the switches to the inputs. So if you have a switch for that LED is on, if you have the switch underneath the LED is on, and then the LED will be on as well. So this is a very simple example. Can show that it works, right? See, I mean, even though it looks super simple, but it goes through the CPU actually, instead of just directly doing the very simple computational logic like we have been doing. Right. So this shows the input and outputs works, right? So it's just sending inputs to outputs, and that's it. And so after you demonstrate that simple example, and you can keep going and try more complicated a really longer examples, assembly examples, right? And we'll talk about the tricks over here really quick during this class. So we have functional examples. I just go through the examples, and most of the code are given. So it's actually, you copy and paste here to your PSM file, right? And then you just compile it and then run it to your IPG and test it. Just play with it. So that's what kind of practice you are getting from the tutorial, right? And for the lab, will be a big task, and will be 2 weeks. To use whatever you learn from here and implement it to the little calculator for the lab. Okay. So now let's look at the in class. We were at so we answered the first one, second one. So KCP SM. It's called constant. So even the first K is not C, but it means constant, coded, programmable state machine, and that's the name of the KCP SM. And also it's ask you what do the following files do, right? So I talked about that just now. The first one is assembler that converts assembly file to a .v file. And the second one, the .v file itself, the KCP.v file itself is a CPU cores module. That's a CPU, right? So if for working for the industry, a lot of companies they don't design their own CPUs, right? Obviously, so they purchase IPs, and whenever during the interviews they're asking like if you want to brag about your experience with using all the different IPs, and that's what they're looking at. If you know how to use certain decoders, very popular decoders, or very popular cores from certain companies, you just can talk about it, because people will just directly buy IPs, right? They just buy IPs and use it and instantiate it in your design, and then you just manage the adding wires, adding other things to manage the timing. So knowing how to use IPs is important. So the .v file is a free IP. You can consider it that way. So the KCP SM6.v is a free CPU IP. In industry, there will be ARM IPs. It will be the same. It will be also a .v file, right? And there will be some peripherals so you can instantiate in your top. So the next one, KCP template, right, provides you with the Verilog templates, examples for the SoC design. So SoC stands for system on chip. It's SoC, right? SoC. System on chip. And the ROM_form.v ensures that the instruction memory is in the .v format. So if you open up the folder you're going to download, right, provided by the developer, and there will be some .htl, .vhdl, actually, .vhdl files, but with the same file names but different extensions. So if you use that one and compile it, so you're getting a VHDL file instead of Verilog file. Just keep that in mind. Okay, don't use a different ROM_form file, right? So you have to use a .v one in order to generate the Verilog format. And following that, there's a example assembly code, and it's going to ask you what are going to be stored in the Z and C flag. So this is a really, I want to say it's a powerful, but compared to C, it's not powerful at all. But for assembly, it is powerful. It enables a lot of things. So the two flags, the zero and carry flags, which is the Z and C flags, right? So if you scroll up and look at the compare instruction, it's over here. So the scroll bar is over here. It's probably close to the top. If you look at the compare instruction, You have two registers, S1, SX and SY, two registers. And when you do a compare, what it's actually doing, you can imagine, it's actually doing a subtraction. So compare instruction, even though it didn't tell you that way, but you can imagine, you can just treat it as SX minus SY for compare. And if that value is 0, then it becomes 0, right? So the Z flag, which is the 0 flag, will be turned on. It's a bit confusing because whenever you got a 0, it's a 0, but Z will be 1. So the way you understand that is, we give a 1 to Z, it's being turned on, right? The flag is on, which means Z, we are getting a 0. So if the return result is 0, the Z flag will be 1. And that is why when SX equals SY, your Z flag will be 1. Okay? So that could be used as a condition, since assembly doesn't have if over there. It's not English, right? It doesn't like C language is English. This is not English. This is assembly. It's a machine code, right? So there's no if. Then you have to check the flags in order to jump to somewhere, right? Like a conditional statement. So that's why these are very useful. And because we are treating it as SX minus SY, so when SX or the first register is larger, if the first one is larger, since we are subtracting the first one, we're doing a SX minus SY, right? So in that case, if XX is larger, there won't be any carry out, because SX is large enough to subtract SY from itself, right? So if the first one is larger, then there's no carry out, which means we don't have to carry out because it's big enough to subtract SY from it. You know what I mean? So in that case, C will be 0. Or, to make it simple, if the first one is larger, C is 0. If the first one is smaller than the second one, you do a subtraction, there will be a carry out. And C will be 1 because carry out will be turned on. So now we come back to the question number 4 over here in class. S1, S2, which one is larger? They're the same. Okay. They're the same. Z should be what? 1. C? 0. Okay, cool. Great. Number 5. Which is larger? Second one is larger. C? 1. Z? 0. Make sense? Number 6. The value stored in the Z and C after the following commands. So for test, it's another instruction. Test. So you can consider that it's actually doing a bitwise AND operation whenever the test instruction is being used. Because this is an 8-bit microcontroller. It's an 8-bit microcontroller. So the registers are 8 bits, right? So the SX and SY, they are both 8-bit registers. So whenever a test instruction is being used, you can consider that it's doing a SY and SX bitwise AND operation. So only if both are zeros, actually not. Do they have to be both like A zeros in order to make the result 0? No. As long as the ones are not at the same location, right? So like 8-bit, 0, 0, 0, 0, 0, 0, 0, 0. Definitely you're getting a 0 for a bitwise AND, right? No doubt on that. However, if you have a 1 here, and you have a 1 here, is a bitwise AND operation result is also 0? Yes. So they don't have to be both zeros. Okay? So this test instruction is actually doing a bitwise AND. And if the result, return result is a 0, Z will be what? 1. Right? Okay? Make sense? And you can see also C is taking in a return result as well. It's taking in what? It's taking in the bitwise XOR for the T. What is T? T is the bitwise result of the 2 registers. So there's a lot of hidden information for assembly, right? It's a user manual. You just have to know it. If you know how this works, then that's it. You know what I mean? So C and Z are the unique flags, and they will be overwritten, and depending on the order of the instructions being operated, being executed, right? So even though, for example, from the compare instruction we just talked about before, they already set and reset the Z and C's, and then after that, you directly execute this guy, and this will override the Z and C's. You don't have multiple Z and C's. This is only Z and C flags in 1 bit. Just to let you guys know. And so for the test instruction, it's doing a bitwise XOR. We are pretty familiar with this one because we have been doing the parity stuff, right? So it's actually, if you have an odd number of 1s in there, you are getting a 1 for C, right? If you have an even number of 1s, you're getting a 0 for C. And that's it. So it's a bitwise AND operation, and eventually you are getting Z and C's being overridden by this instruction. So in that case, if you look at number 6, right? Number 6. What are the values stored in Z and C after the following commands? So I didn't say anything about S1, but if S1 is the first time being used, it's a register and it should be all zeros. Okay, it should be all zeros. And in that case, if I'm doing a S1, do a bitwise AND with 0, 1, and it has to be a hex, right? So 0, 1 is a hex. By default, it's a hex. So it's actually 4 zeros and 3 zeros and 1 little 1 there, right? So it's a 0, 1, like that. So 7 zeros and little 1. So it becomes, because S1 has 8 1s and 0, 1 has 7 zeros. Oh, what did I say? So S1 has 8 zeros and 0, 1 has 7 zeros and 1 1, right? If you do a bitwise AND, is the result 0? No. No, result is not 0. Result is, yeah, it's 0 actually. Sorry.
So confused.
Yeah, it's 0. So in that case, answer Z should be 1, right? Z should be 1. And C should be what? 0. Because even, right? Even. Cool. Because I have an incorrect solution here. Number 7. Toggle bit 5. So bit 5 is actually the 6th bit from the right. And send the result to S0. Toggle a bit and send it back to a register. So remember how we toggle a bit? How we toggle a bit? Like if statement. If it's a 0, give a 1. If it's a 1, give a 0. We don't do that. We don't do it that way. How to toggle a bit?
Not.
Not. How to extract it though? It's a 1 little bit in the byte, right? you're not toggling everything. You're not doing a bitwise knot. You have to target that little bit and toggle it.
You do like a test instruction with another binary number where the same bit you're comparing is like a 1 or a 0 based on what you want.
Cool. I believe that will work actually. Multiple lines of code, right? But think about when we do a two's complement calculator, how did we flip everything for two's complement? Yeah, XOR actually, right? Yeah. So the XOR with what? With 1, right? Okay. So in that case, you can have a mask, right? It's a mask, and all the other bits are just zeros because XOR with zeros are still that thing, but just that bit 5 has a little 1 there, right? So do a bitwise XOR and eventually giving you only that bit is being toggled. So let's see if there's an instruction just for that. See here? It's actually just one line. Because after the XOR execution or operation, you send it back to the first register. So it just works perfectly for this operation here. So these are all the tools in the toolbox for how to program the CPU, right? So what is instruction set? Instruction set is actually all the tools in the toolbox that you guys can modify and give you all the flexibility and capability to jump, to compare, to and all these kind of things. And these are implemented by the corresponding hardware inside. You just have to have the hardware first, and in order to have that instruction set available, right? Number 8. Use assembly code to clear bit 1 of S1. Clear it and send a result to S0. How do you clear? It's still a mask, right? How do you clear a bit? And right? And you just place a 0 at that certain bit, certain location, and do an AND, bitwise AND. How do you send it to somewhere? I mean, for different architectures have different instructions, and sometimes you are doing move, right? Did you learn move was that move, MOB in your architecture class? No.
It was like LW.
Oh, load.
Yeah. Load word.
Okay. So that's RISC-V, right? Okay. So I think the Intel ones, these are MIPS, right? The MIPS something. The MIPS architectures are doing move, MOV, similar stuff, right? So similar stuff. So the load is loading from right to left, right? Loading from right to left. Let me see where's the load. So the load instruction should be the first one you should know. And here, right? So when you load it, you load a register from the right to the left register. That moves data between the two registers. You can also move a constant. You can't do whatever you want to do, right? So if it's a register, 2 registers, which is fine. You have a constant on the right and register on the left, which is fine too. But you cannot flip it, right? Cannot flip it. So you just have to use whatever they tells you to do. You cannot just change whatever you want to change. And for store, because load, you are loading something to a register, and you can also store, right? Store. So for store, it's from left to right, and it enters a memory instead of just a register itself, but it's taking this SY's value as a address of the memory. So it's actually, you can write into the RAM instead of just a register available there. Okay, you can put in the RAM, and this register will hold the address of it. So if you see a parenthesis here, that means the register's value is a byte, right? It's a byte, but that byte is not a data, it's a address. So whenever the parenthesis shows up, the internal register represents the address, and it's ready into the memory. For fetch, it's the opposite way, but similar concept. This will be the address, and this will be it's gonna taking out something from the memory and from this address. Okay. So that was number 8, right? Clear one. Yeah. Then number 9, to set bit 0 and send the result to S0. Very similar to number 8. How to set a bit? You OR it with 1, right? OR it with 1. So find a mask for that operation, and you do an OR logic, and then load it to a different register. Because S1 and S0 apparently they are different registers. So I have to do everything in the S2 register first, and then load it to the S0 register. Number 10, use assembly code to check bit 7 of S0. If result is 0, assign S0 to S1. Otherwise, go to address symbol, done, and do nothing there. So it's a symbol. Let me see if there's an example here. Jump, right? Like these ones. So you can have a subroutine by giving a label. For example, that's your main program, right? It's like a main parenthesis or loop parenthesis, like what you have been using in Arduinos, right? So it's doing operations, and this code doesn't make sense, but it just shows you how that works. So it's gonna run this guy, and if it immediately calls this subroutine, it will directly jump to that subroutine. So you have to label it with routine with a calling here, whatever name you will name it, which is fine. You have to have a calling here, which just shows the starting point of the subroutine, and it runs these ones, and then you have to put a return here, so it's able to return back to this guy. Okay, but the thing is, after running this one, it will keep running the following instructions, and whenever it reaches this point, it will still run it. So I have to keep that in mind. Have to keep that in mind for a design. If you just want to jump to somewhere and don't want to come back, or it comes back but you don't want to run this subroutine after it comes back, you have to design it in a certain way. Okay. You could add another jump, right? So whenever it reaches here, it jumps to another place and has like done or something and call it, and with nothing underneath it, and it won't return back. So it doesn't like the Arduino loops, right? It comes back and forth. It's always coming back and rerun it. And that's what the major the mainstream microcontrollers are doing, right? You can either have a main function, have a loop function in your C code, and always come back. It always comes back. But for assembly, if you don't ask it to come back, it won't come back. It will just stuck there and stop. Okay, so you have to design a loop by yourself in assembly. It won't run back and forth by itself. Okay, so for the example code, a very simple example, right? If it's not coming back, how could we create a simple loop? And that's how I create a simple loop, right? You jump back. So then do it again and jump back. Just keep doing that. That's how you create a loop. Alright? Just keep that in mind. So let's take a look at the number 10 again. So use assembly code to check bit 7. How to do that? Test. If result is 0, I think the result means bit. Wait. Yeah, because you can. Wait.
Check bit 7 that's 0.
I'm just trying to think of if I'm trying to ask you guys for that bit or for the whole thing, for the whole result. Is there any difference? How would you do that? How would you approach this?
If you do it with test, you're gonna get 2 bits out when you compare it.
2 bits? 2 bytes or 2 bits?
2 bits.
Why 2 bits?
Because CC.
Oh yeah. But C is not being used here, right? Why C is being used? You're only looking at 0 or not, right?
Yeah, you're right.
So if you do a test, for example, do a test. So which mask would you like to use for this case? So S0, we don't know what the bits are, right? It's just like a byte over there, and we are trying to see if bit 7 is 0, but do we care about other bits? Probably not. So we only care about the bit 7, which is the MSB actually, because it's from 0 to 7, right, for the byte. So we're actually only care about the so basically this is very useful because sometimes you are checking certain bits of the byte and see if it's 0 or 1. This is the only 2 conditions you may have. So it's trying to check the MSB, see if the MSB is 0. If you do a test, what's going to happen? If you do a test, right? So what kind of mask would you like to use here? As is the register, right? So you have a byte. I don't care about the 0 to 6, right? It's bit 7, right?
1, 0, 0.
I don't care these ones. I want to see if this is 0. If I do a test, I don't care about these ones, so I just give zeros to it. The reason for that is because the final result is only looking at if it's 0 or not, because test is doing and logic, and if it's not 0, you wouldn't be able to see. So if you give a 1 here, right? Give a 1 here. And the test operation is looking at the final result. However, we only care about this bit. That doesn't matter because if this the bitwise AND is giving you a T, right? T as a result, if this becomes 0, right? If this is 0, then Z will be 0, right? Well, Z will be 1. Sorry, Z will be 1. Is that right? So if this is 1, Z will be
0.
0. So this is a pretty valid mask that we can use for this test operation. In that case, you can just directly give us what is that 0? Is that 8? Yeah, it's 8. 8 0, right? 8 0 will be the mask. And how do you check the condition though? You look at the options you have. Scroll up. Where are these ones? jump instructions. It's up there. That's right.
You can jump if
You can jump Z, right? Jump Z.
you don't want to load.
Because Z is right you got a Z there at the output over there, right? So you can do a jump Z. So if you have an NZ or NZ, right? So Z means Z is 1. NZ means not Z, which is not Z is 1, right? So actually, if you do jump Z, right? So look at the description of the problem. If the result is 0, do assignment, right? If the result is 0, Z will be 1, right? So Z will be 1, then you assign, then you do a load. Right? It becomes, because after this one, Z will have the result already, right? Then if you do a jump,
Are you saying the result is Z or the result is the 7th bit of S0?
you cannot use that one as a condition. That's a problem, right? So we can only jump Z. You cannot jump that bit.
Well, I know, but in the question, are you saying the result is 0? Or are you saying that that's like when the 7th bit S0 is 0?
I
Because
think
isn't it it's kind of inverted?
Mm.
If you have a 0 there, then you get a 1 for Z.
Yes. Yeah. But for the condition, you're checking Z, right?
Yeah.
Condition, you're checking Z.
Right.
If Z is 1, then the result is 0. And that's what the description says.
Okay.
If it's a 0, if the result is 0, which is actually the result, not the Z.
Got it. Okay.
Yeah, that's right.
So then you want to use NZ.
Then you need to jump, right? Then you jump. So if you do a jump Z to do something, right? This is just English, right? English is a label. And you have to do something here. Colon, right? Do something. What you do here? Load, right? Load. Load S0 to S, assign S0 to S1. So it's going to be S1, S0. So loading S0 to S1 to do something. Right? Because if the result is 0, you do that. Otherwise, go to a symbol done and do nothing. So where should you place that? That's the question here.
Like do something.
No, do nothing. This is do something, right?
Oh.
Sorry. Do something. No space, right? It's just English. Do something, right? Do something. Do something. Jumps here, right? Do it. So how do place do nothing? So first, do nothing should be a place with nothing over there, right? Let's just put this here, done, and nothing. Just don't do anything here. Which is fine because you place this one underneath this one, and eventually it finishes this guy, and will eventually go to done. It's finished. It's not doing anything else, right? This is already executed. But the thing is, only.
Well, wouldn't it still execute?
No, I mean whenever Z is 0, we don't want to execute this guy, right? We want to directly jump to here, and then there's nothing else underneath it. So that's why you want to flip it. You know what I mean? If you put done above this guy, then whenever done is being executed, we'll sequentially to the next one. We'll still execute this one. So put the done at the very bottom, so there's nothing below it, because it's running from top to bottom. So these instructions, because assembly is really super old technology, right? So these ones, but still being used. I mean, it's not meaning it's not useful for bottom level design and the digital designers. We still use assembly a lot in the industry. But the thing is, it's like a snapshot, right? So everything will be converted into machine code, and they will be just stored in the same sequence in your instruction memory. So they're taking every instruction one by one, take it out, and executing the CPU. It's really traditional code. It's very close to the bottom level of the machines. So where should we put our jump to done to a different place though? Is this done? Is this all completed or not?
You should do jump NZ to done,
Jump NZ to done.
and then get rid of the do something.
I think that works too. That works too. That's the second method, right? So if you do jump NZ and done, it jumps here. If it's not, otherwise you directly do this one and then done, which is nothing. We'll still do the job, right? However, if you so that's a good method. That's a method too. You can consider that way. If you do a jump D, jump Z instead. So whenever Z is 1, we'll do this one, do here and finished, right? If it's not, this is not being satisfied, it's going to do the next. And we don't want to run this, execute this guy. So what should we do? Plug in something in the middle, right? Before it. Right? So otherwise, I mean, you can directly just do a jump, right? Just jump. Jump to where? Just directly jump. Done, right? That's it. Just directly jump to done. That's it. See if there's an option like this over here. Directly jump to a subroutine. Is there a?
It's just an
Oh yeah, the first one, right?
unconditional jump.
Yeah, just the first one. That works too. All right. Number 11. Extract a bit of a register and load it to a different register. How to extract a bit? Seems like you are extracting it, but it doesn't really matter. I mean, $1 is $1. I don't really care. I say $1 million is $1 million. I don't care who gave me, right? It could be from the college, from you guys. It's okay. I'll just keep it. So it doesn't matter. It's extracted directly from that register, or it's just giving to it, right? Giving to it. So what could you do? Bit 5 is actually the 6th bit, right? The 6th bit.
You can get it with an and.
Yeah, you can do a test again, right? Do a test again. But what kind of mask would you like to use? If you do a test, I'll let you guys think about it. If you do a test, right, just for that bit 5, you put a 1 there, but all the rest of the bits are all zeros for the mask. And then if the final result is 0, which means that bit from S0 will be was 0, and then you can use the Z as a condition, right? So you can jump Z. If it's a 0, jump Z to you load a 1, right? You load a 1. Wait, if it's a 1, you do nothing, right? Because if a Z is 1, which means it was a 0, you just don't do anything to it. We're assuming that I mean, extract that bit. We're assuming S2 originally was 0, all zeros. Okay? Let's make it that way. So if Z is 1, we don't do anything to S2 because S2 originally is 0. We don't have to do anything to it. Just do nothing. Otherwise, we have to load a 1 to it. We load a 1 to it. It's actually not extracting, it's just looking at it, right? So if it's a 1, give a 1 to it. If it's a 0, give a 0 to it, to S2. And make sure that after done, you shouldn't do anything else over there because that's the end of the program, right? Clear? Questions? Number 12. That's the shift trick here. It's quite powerful. It's over here, and you only need to care about 1/2 of it because it's just either shifting to the left or shifting to the right, but with different modes. Even though there are 10 different ways, but you only need to care about one of them, right? Because the other one will be the same. So it's basically shifting right, shifting left, right? So SL will be shifting left, and SR will be shifting right, and they are being labeled as 0, 1, X, A, R. Similarly for the left shifting as well. So now let's just look at the shifting to the right one. Make it less overwhelming. So I think we are looking at let's look at the first one first. So when you do a SR0, it's do the shifting and shifting the LSB to C. Okay, so you can do a condition check because the C is being changed, right? So that's the flag. And 0 will be replaced. No, 0 is going to replace the MSB, so everything is shifted to the right by 1 bit, right? And the LSB goes to C, so you are not losing it, right? Which is fine. I mean, it's just something to make it available, make the LSB available, so you can use it for some reasons, right? And shift right, number 1 mode, it's adding a 1 to MSB. Okay. There must be a application to it. I don't know yet. I haven't used it yet.
2's complement shifting.
2's complement shifting.
I don't know.
Yeah, adding a 1 to the MSB definitely reminds you about the 2's complement, changing the sign, right? But why you're adding a 1 to it? But there must be some way to use it, for some of the computations. Anyway. And for SRX, it's shifting to the right, but X. So again, LSB goes to C, goes to carryout, and it's duplicating 7 to the. So it's not losing it; it's just duplicating it, which is good. Like a 2's complement. If you're duplicating the MSB, you're not actually changing the value of it, right? You're not changing the value of the number. But whenever everything being shifted to the right. Are you changing it? You are, because you're losing the LSB. Anyway, so it's just the operation to let you know, okay? If in case you find an application to it, which is great. It shows you that they can do it. All right. SRA. It output the LSB to C, and at the same time, it put the previous C into the MSB. It's pretty interesting. So it's like a shifting in the loop. Shifting in the loop. Are you losing anything? Probably the first time, because the first time, no, you are not losing anything because the byte is only 8 bits. You are adding a C to it, it's forming a 9 bits stuff, and C was placed into MSB, right? But eventually your LSB goes to C, and the next time you shift again, it just keep going as a loop. It's like you have a temporary buffer. It's holding the bits being shifted out, and you are not losing anything actually. But eventually you have a C. The extra C being put into here, but if you shift it one more time, it's being shifted out. You can always recover your byte, right? So RR, it shifts out LSB to the carry out bit, and then at the same time that LSB is being placed as MSB. So you are not losing the LSB, but at the same time, LSB goes to the MSB as well. So very similar to this one, but the thing is, it's not directly placing your C back to the MSB. However, it places the LSB to the MSB. So okay, so these are all the tools we have, right? So look at the problem number 12. It's a 16-bit It's a 16-bit binary number that is stored in the S0, S1. So this is another example showing that, I mean, this is a very simple computer system. It's 8 bits, right? So the 8 bits can only represent if it's unsigned from 0 to 255, right? 0 to 255. So definitely we can use larger numbers than that. So you have to use multiple registers and treat them as an upper byte and lower byte to form a 16-bit number or a bigger number, right? So, but these are all registers bytes, no different, but you treat them in different way to form a larger number. So as a 16-bit binary number, you have to use the 2 bytes to store them. I put them in S1 and S0. And if you do a concatenation as S0, S1, you can form a 16-bit number. So use assembly instructions. So a concatenation is not a format that can be used in assembly, just like you guys know. It's just showing you that, it's upper byte, lower byte. So that asks you to use the assembly instructions to shift the 16-bit number to the right by 1 bit. It's two registers, and the first register is considered as a higher byte, and the second one is a lower byte. And after shifting, this should still be the same way, right? So S0 still holds the upper byte as well. How would you do that? The thing is, the higher bytes LSB has to go to the lower bytes MSB, right? Because the 2 bytes, right? The 2 bytes are here. They're actually like this, but the thing is, they have to be placed in the 2 bytes, right? So here's the LSB. Consider they are the 16-bit like this. So the LSB of the first byte will have to go to the MSB of the second byte after shifting. You know what I mean? But they are in separate registers. How would you do that? So by looking at all the options we have. I mean, for normal shifting, usually the MSB of the higher byte will be replaced by what? 0. So the first one should be SR0, right? So you do SR0 and followed by S0. And what happened for the LSB? What happened to the LSB? Go to C.
Do you like SRC?
Then SR what?
Well,
there's no SRC. That's a
have
new
SRX. Instruction
though. SR what?
X.
SRX.
Is that what that does? Do you get to
I mean, for the lower byte, what do we want for the lower byte? Just because the higher byte already shifted out the LSB to C, right? And remember what I told you, the LSB of the higher byte needs to go to the MSB of the lower byte. So now the LSB of the higher byte is in C. So where should you take that MSB from for the lower byte? Tongue twister? Running out of time for the class?
Would you want to use SRA then?
That's all right, yes. Because it's taking C, that stores the previous C from the first instruction, and place it to the MSB of it. And you don't care about the LSB over the lower byte because it's gone.
So that C stays the same between separate instructions.
Yeah, it's just 1 bit.
So it's
it
just
stay-
like
it
one
stay-
dedicated bit across our whole
Yeah,
system.
yeah,
Okay.
yeah. Make sense? All right, number 13. I'll give you a couple minutes to get it done. Is that reasonable amount of task? Similar to implement this control structure in C, right? So that's if it is larger, add a 1 to it, otherwise do nothing. Comparison, right? Compare should be a compare instruction. Right, take a couple minutes to work on it and then turn it in. And we just perfectly finished all the questions over here in class.